In section 7.5, we're going to look at multiple angle formulas as well as product to sum and sum to product formulas. The first ones we're going to start with are the very popular double angle formulas. These get used a lot in trigonometry and also in other classes. These tell us how to find the sine, cosine, and tangent of 2 theta based upon single function thetas. For example, we know that the sine of 2 theta is equal to 2 sine theta cosine theta. The cosine of 2 theta is equal to cosine squared theta minus sine squared theta. And the tangent of 2 theta is equal to 2 tangent theta divided by 1 minus tangent squared theta. In example 1, suppose we're told that the sine of theta is equal to 5/13 and theta lies in quadrant 2. We are asked to find the exact value of each of the following. We want to find the sine of 2 theta, the cosine of 2 theta, as well as the tangent of 2 theta. In order to find the sine of 2 theta, again, from above, we have a formula for this. The sine of 2 theta is equal to 2 sine theta cosine theta. So if I knew the value of sine theta and cosine theta, then I could find the value of sine 2 theta. Well, this is very similar to a problem we've done in the past. We know the value for the sine of theta, so that part we already know. All I need to know is find the value of the cosine. And to do that, we can use our Pythagorean identity that relates the two, and that is that sine squared theta plus cosine squared theta is equal to 1. I can plug in my value for the sine of theta, that's 5/13. So 5/13 squared plus cosine squared theta should be equal to 1. 5/13, if we square that, we're going to get 25/169 plus cosine squared theta equals to 1. I want to get the cosine by itself, so I'm going to subtract 25/169 from both sides. Here these would cancel. We're going to get cosine squared theta is equal to 1 minus 25/169. Get common denominators and subtract is going to give us 144/169. And then to get the cosine by itself, we're going to take the square root of both sides. Now we have to be careful because when we're taking the square root of both sides, we know that a value could have either a positive or a negative square root. And this is where this additional information is going to come into play. We are told that theta lies in quadrant 2. From our all students take calculus, we would know that in quadrant 2 that this cosine is going to be negative. So this is actually going to be a negative square root of 144/169. And therefore we get that the cosine of theta is going to be equal to negative 12/13. So we were told that the sine of theta is 5/13. We now know that the cosine of theta is negative 12/13. And with that information, we should be able to finish off this problem. So for the sine of 2 theta, this is going to be equal to 2 times the sine, which is 5/13, times the cosine of theta, which is negative 12/13. If we multiply that all together, 2 times 5/13 times negative 12/13, that should give us negative 120/169. Let's now find the value for the cosine of 2 theta. The cosine of 2 theta, according to our new identities, this is equal to cosine squared theta minus sine squared theta cosine of theta is negative 12/13. The sine of theta, we were told, is 5/13. Negative 12/13 squared is positive 144 over 169. 5/13 squared is 25 over 169. Luckily, we already have a common denominator, so we can just go ahead and subtract. If we do 144 over 169 minus 25 over 169, we should get 119 over 169. We are almost done. For the tangent of 2 theta, you could either do one of two things. We do have a double angle identity for the tangent of 2 theta. It's 2 tangent of theta divided by 1 minus tangent squared theta. We already know the sine and the cosine, so we could very easily find the tangent of theta and plug it into that. Or we could just use one of our simple quotient identities. We know that the tangent of an angle is equal to the sine of that angle divided by the cosine of that angle. Therefore, the tangent of 2 theta is going to be the sine of 2 theta divided by the cosine of 2 theta. That was the answer to our 2 previous parts. The sine of 2 theta was negative 120 over 169. The cosine of 2 theta was 119 over 169. And then we can just simply go ahead and divide those two. Good fraction arithmetic, keep, change, flip. The 169's cancel, and we get that the tangent of 2 theta is going to be negative 120 over 119. Let's take a look at the next example. In example 2, we're asked to find the exact value of 2 times the tangent of 15 degrees divided by 1 minus the tangent squared of 15 degrees. Well, 15 degrees, this isn't one that's on our unit circle, so it wouldn't be ratios we'd be expected to memorize. But if you look at the form of this, this exactly fits into the form for the double tangent angle formula. This would be equal to the tangent of twice 15 degrees, which would be equal to the tangent of 30 degrees. And that's one that we should be able to find the exact value of. We know that the tangent is the sine over the cosine. So it's going to be the sine of 30 degrees over the cosine of 30 degrees. The sine of 30 degrees is 1/2. The cosine of 30 degrees is radical 3 over 2. Keep, change, flip. You would get 1 over the square root of 3, which would rationalize to square root of 3 over 3, which would be the exact value. It turns out that there's more than one formula that can be used for the cosine of 2 theta. So we have several double angle cosine formulas. Depending upon the individual problem you're working on or your setup, any one of these 3 could be helpful depending upon the circumstances. The first one is that the cosine of 2 theta is equal to cosine squared theta minus sine squared theta. That's one we saw just a moment ago. We also have that the cosine of 2 theta is equal to 2 cosine squared theta minus 1. And it's also true that the cosine of 2 theta is 1 minus 2 sine squared theta. Let's take a look at the next problem. Here they ask us to verify the identity that the cosine of 3 theta is equal to 4 cosine cubed theta minus 3 cosine theta. So let's go ahead and start off this one. We've already worked on a bunch of these in previous sections. Ideally, we said that generally what you would want to do is start with the quote-unquote more complicated looking side and try to transform it into the other side. Here, if we look at the left-hand side, what makes this one perhaps more involved with more stuff to do is that it doesn't involve just a basic angle theta. We actually have the cosine of 3 theta, whereas on the right-hand side you have just a cosine cubed of regular theta minus 3 cosine of theta. Now this whole section so far has been all about double angle identities, but this is a triple angle. So we can look at it and say, well, what could we possibly do here? Well, one thing we might be able to do is use our sum difference identities from the previous section. For example, I can think of the cosine of 3 theta as being 2 theta plus an additional theta, where theta would be our basic variable, and then the 2 theta would be like the new variables we're working with right now in this double angle section. So let's go ahead and apply our rule for the cosine sum formula. If we have the cosine of the sum of two angles, in the notes this would be like the alpha and beta from the previous section. According to that formula from before, it should be equal to the following. It's the cosine of the first thing, that's the cosine of 2 theta, times the cosine of the second angle, that's theta, and then we're going to have a minus the sine of the first angle, that's 2 theta, times the sine of the second angle, which is theta. From here we could ask the question, well, what do we do next? Let's try to eliminate now some of these double angles. We want to try to get rid of the cosine of 2 theta and also the sine of 2 theta, which we have from formulas in this section. Now we have a wide variety of formulas here to choose for the cosine of 2 theta. In terms of which one we should choose, there's no right or wrong answer, but let's try and choose a little bit intelligently based upon what we're trying to end up with. If I look at this identity that we're trying to verify, one of the things that I notice is that right-hand side only involves the cosine function, so it only has cosines in it. So it might make sense that if I'm going to come up here and select a cosine of 2 theta formula, I might want to choose the one that only involves cosines itself, which would be this one right here. So everywhere we see the cosine of 2 theta, let's replace it with 2 cosine squared theta minus 1. So this is going to be 2 cosine squared theta minus 1 times the cosine of theta minus, now we only have one formula for the sine of 2 theta, that was 2 sine theta cosine theta. That swaps that part out, and this is still going to be multiplied by the sine of theta. And so far this is good for us because, again, if you're trying to verify an identity, you should be continually asking the question, how is what I have similar and how is what I have different from what I'm trying to show that it's equal to? Well, the good news now is that this step right here, so right where we're at, we no longer have any multiple angles. Everything is just a function of the angle theta, which at least makes it a lot more like the right-hand side. One thing we don't have on the right-hand side is any kind of parentheses, so now let's go ahead and distribute to get rid of these parentheses. I can distribute a cosine of theta into this first parenthesis, in which case I'm going to get a 2 cosine cubed theta minus cosine theta. I can distribute, not really distributing, but just multiplying these two together. I have sine times sine, which will give me a sine squared theta, cosine theta there. Looking good. The one thing that we said is that, again, how are they similar, how are they different? On the right-hand side, I only have cosine terms. Right now, I have one sine term as a part of this. That's sine squared of theta. That we can get rid of using a Pythagorean identity. Remember the Pythagorean identity that sine squared theta plus cosine squared theta equals to 1. I can solve that identity for sine squared to get the following. This is 2 cosine cubed theta minus cosine theta minus 2 times sine squared theta is 1 minus cosine squared theta times cosine theta. And now distribute the negative 2 and then distribute the cosine, and we should get the following. This is going to give us 2 cosine cubed theta minus cosine theta. I'm just going to kind of imagine for a moment. Just imagine if that cosine was moved around to the front. I'm going to distribute a negative 2 cosine theta into this parenthesis. Negative 2 cosine theta times 1 is negative 2 cosine theta. And then a negative 2 cosine theta times a negative cosine squared theta will give us a positive 2 cosine cubed theta. And then from here we have some like terms we can combine. 2 cosine cubed plus 2 cosine cubed will give us 4 cosine cubed theta. And a negative cosine theta minus a 2 cosine theta will give us a negative 3 cosine theta. And just a quick check, that's exactly what we were aiming for. So we have essentially verified the identity.